Florida's newly adopted residential code shares similarities with New York State's code by using NFPA 70A as its foundation for electrical requirements. However, Florida's approach is distinct due to its decision to reserve chapters that are commonly dedicated to electrical specifications in other codes. This reservation suggests a possible future transition toward directly implementing NFPA 70 and subsequent revisions. Florida's residential code references NFPA 70 to define electrical system requirements, but it also permits the use of alternative methods and materials that are detailed within NFPA 70. Chapters 34 through 42, which are traditionally the home of electrical requirements in many other codes, are specifically marked as reserved in Florida's code. It's worth noting that the report concerning Florida's code identifies the National Electrical Code as a reference standard rather than making a direct reference to the ICC Electrical Code. The ICC General Committee has put forth a proposal to reform the International Building Code, which would incorporate provisions and references derived from NFPA 70. This proposed change has the potential to bring the International Building Code into closer alignment with Florida's existing approach. Currently, Florida is operating under the 2002 edition of the National Electrical Code, and the adoption of the 2005 edition is not expected to occur before July 1, 2006. This video breaks down the key points of Florida's adoption of NFPA 70 and the implications for electrical work within the state. Firstly, we will examine the specifics of NFPA 70 and its role as the foundation for Florida's electrical requirements. NFPA 70A, officially known as the National Electrical Code Requirements for 1 and 2 family dwellings, is a streamlined version of the National Electrical Code specifically tailored for residential applications. It includes the most common wiring methods and materials encountered in the construction of single-family and two-family homes, making it a practical choice for states seeking to simplify their residential electrical codes. Secondly, we will analyze the significance of the reserved chapters in Florida's residential code and what this could mean for future revisions. The decision to leave chapters 34 through 42 reserved is a clear indicator that Florida is considering a more direct approach to electrical codes, potentially integrating the full National Electrical Code, NFPA 70, in the future. This move could streamline the code adoption process and ensure consistency with national standards. Thirdly, we will investigate the implications of Florida's reference to the National Electrical Code as a reference standard rather than adopting the ICC Electrical Code. This decision signals a preference for the National Electrical Code as the primary source of electrical standards in Florida. It also highlights the ongoing debate between the National Electrical Code and the ICC Electrical Code, as different jurisdictions weigh the benefits of each. Florida's decision to prioritize the National Electrical Code could influence other states to follow suit. Finally, we will assess the timeline for adopting the 2005 National Electrical Code in Florida and the reasons for the delay. The adoption of updated electrical codes is a complex process that involves legislative review, public comment periods, and training for inspectors and contractors. Florida's projected timeline for adopting the 2005 National Electrical Code reflects the need for thorough preparation and stakeholder engagement to ensure a smooth transition. Now let's delve deeper into the key aspects of the National Electrical Code and NFPA 70A. The National Electrical Code, NFPA 70, is a comprehensive set of standards that govern the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years by the National Fire Protection Association and serves as the foundation for electrical codes in most states and municipalities. NFPA 70A, as mentioned earlier, is a condensed version of the National Electrical Code that focuses specifically on the requirements for 1 and 2 family dwellings. It includes the most common wiring methods, materials, and safety provisions relevant to residential construction. While NFPA 70 simplifies the code for residential applications, it still references the full National Electrical Code for more complex or specialized installations. The National Electrical Code covers a wide range of topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It provides detailed requirements for conductors, cables, raceways, boxes, and other electrical components. The National Electrical Code also addresses safety issues such as arc flash hazards, surge protection, and emergency systems. In addition to technical requirements, the National Electrical Code includes administrative provisions that outline the roles and responsibilities of electrical inspectors, contractors, and other stakeholders. It also establishes procedures for code enforcement, permitting, and appeals. Now let's examine the reserved chapters in Florida's residential code and the potential implications. Chapters 34 through 42 of the International Residential Code typically cover electrical requirements such as general requirements, branch circuit and feeder requirements, wiring methods, equipment installation, and swimming pools. By reserving these chapters, Florida has effectively removed these provisions from its residential code and instead relies on NFPA 70A and the National Electrical Code for electrical installations. This decision suggests that Florida may be considering a more streamlined approach to electrical codes, potentially eliminating redundancy and inconsistencies between the residential code and the National Electrical Code. It also opens the door for future revisions that directly incorporate the National Electrical Code into the residential code, making it easier for contractors and inspectors to navigate the requirements. However, reserving these chapters also raises questions about the scope and applicability of the residential code. It is important for users to understand which electrical requirements are covered by the residential code and which must be obtained from the National Electrical Code. This can create confusion and increase the risk of errors if not properly addressed. Now, let's discuss the significance of Florida's reference to the National Electrical Code as a reference standard. By referring to the National Electrical Code as a reference standard, Florida is acknowledging its importance as a source of electrical standards while maintaining some flexibility in how it is applied. This approach allows Florida to adopt specific provisions of the National Electrical Code that are relevant to its needs while avoiding unnecessary or overly burdensome requirements. It also allows Florida to incorporate other standards or best practices that are not explicitly covered by the National Electrical Code. However, this approach also requires careful coordination between the residential code and the National Electrical Code to ensure that all electrical installations comply with the applicable requirements. It is important for users to understand the relationship between the two codes and how they interact with each other. Now, let's consider the timeline for adopting the 2005 National Electrical Code in Florida. The adoption of updated electrical codes is a complex process that involves multiple steps and stakeholders. Firstly, the National Fire Protection Association publishes a new edition of the National Electrical Code every 3 years. Secondly, state and local governments review the new edition and consider adopting it into their building codes. Thirdly, the adoption process typically involves a public comment period, during which interested parties can provide feedback on the proposed changes. Fourthly, the code adoption process may also involve legislative review and approval. Finally, once the new code is adopted, it takes time for contractors and inspectors to become familiar with the changes and implement them in the field. Florida's projected timeline for adopting the 2005 National Electrical Code reflects the need for thorough preparation and stakeholder engagement to ensure a smooth transition. The delay in adopting the new code may be due to a number of factors, including the complexity of the code changes, the need for training and education, and the availability of resources. In summary, Florida's decision to rely on NFPA 70A and the National Electrical Code for electrical requirements in its residential code is a significant development that could influence other states to follow suit. The reserved chapters in the residential code suggest a possible future transition towards directly incorporating the National Electrical Code, while the reference to the National Electrical Code as a reference standard allows for flexibility in its application. The timeline for adopting the 2005 National Electrical Code reflects the need for thorough preparation and stakeholder engagement. Let's expand on specific sections within the National Electrical Code that are particularly relevant to residential applications and frequently encountered in 1- and 2-family dwellings. We will discuss grounding and bonding requirements as they pertain to residential electrical systems. Grounding and bonding are essential for electrical safety. The National Electrical Code Article 250 provides detailed requirements for grounding and bonding electrical systems to ensure a low impedance path for fault current, which facilitates the operation of overcurrent protective devices like circuit breakers and fuses, thereby reducing the risk of electrical shock and fire. In residential settings, the grounding electrode system typically consists of a metal underground water pipe, a ground ring, or ground rods or plates. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the service equipment. Bonding ensures that all metallic parts of the electrical system are electrically connected to create a continuous low impedance path. This includes bonding the service equipment, metal enclosures, metal raceways, and non-current carrying metal parts of equipment. Specific requirements for bonding include the use of bonding jumpers to connect metal parts and the proper sizing of bonding conductors based on the size of the overcurrent protective devices. Next, we will cover branch circuit and feeder calculations as outlined in the National Electrical Code Articles 210 and 220. These articles provide the methods for calculating the required ampacity of branch circuits and feeders, ensuring that they are adequately sized to handle the expected load. In residential applications, branch circuits are typically rated at 15 amps, 20 amps, or 30 amps, depending on the type of load they serve. General-purpose branch circuits that supply lighting and receptacles are typically rated at 15 amps or 20 amps. Appliance branch circuits that supply specific appliances such as refrigerators, washing machines, or dishwashers are typically rated at 20 amps or 30 amps. The National Electrical Code requires that branch circuits be protected by overcurrent protective devices such as circuit breakers or fuses that are rated no higher than the ampacity of the circuit conductors. Feeders are the conductors that supply power from the service equipment to one or more branch circuits. The National Electrical Code provides methods for calculating the feeder demand load, which takes into account the fact that not all connected loads will be operating simultaneously. The feeder demand load is used to determine the required ampacity of the feeder conductors. Also important are wiring methods. National Electrical Code Chapter 3 covers various wiring methods that are commonly used in residential applications. These include non-metallic sheath cable, commonly known as NM cable, which is widely used for branch circuits and feeders in dwellings. NM cable consists of two or more insulated conductors enclosed within a non-metallic sheath. It is relatively inexpensive and easy to install, making it a popular choice for residential wiring. The National Electrical Code specifies the types of NM cable that are permitted for different applications, as well as the installation requirements for NM cable. Another common wiring method is electrical metallic tubing or EMT. EMT is a thin-walled metal raceway that is used to protect conductors from physical damage. EMT is typically used for exposed wiring in basements, garages, and other areas where the wiring is subject to physical damage. The National Electrical Code specifies the types of EMT that are permitted for different applications, as well as the installation requirements for EMT. Other wiring methods that may be used in residential applications include flexible metal conduit, liquid-type flexible metal conduit, and rigid metal conduit. Each wiring method has its own advantages and disadvantages, and the choice of wiring method will depend on the specific application and the requirements of the National Electrical Code. The National Electrical Code Article 310 addresses conductors for general wiring. This article provides requirements for the types, sizes, and ampacities of conductors used in electrical wiring. Conductors are typically made of copper or aluminum and are insulated with various materials, such as thermoplastic, thermoset, or rubber. The National Electrical Code specifies the types of conductors that are permitted for different applications, as well as the ampacities of conductors based on their size and insulation type. The ampacity of a conductor is the maximum current that it can carry continuously without exceeding its temperature rating. The National Electrical Code provides tables that list the ampacities of conductors for various insulation types and ambient temperatures. It is important to select conductors that are properly sized for the load they will be carrying to prevent overheating and potential fire hazards. Overcurrent protection is covered in National Electrical Code Article 240, which provides the requirements for overcurrent protection devices such as circuit breakers and fuses. Overcurrent protection devices are designed to protect conductors and equipment from overloads and short circuits. Circuit breakers are automatic devices that trip and interrupt the circuit when an overcurrent occurs. Fuses are one-time devices that melt and interrupt the circuit when an overcurrent occurs. The National Electrical Code specifies the types and ratings of overcurrent protection devices that are permitted for different applications. It also requires that overcurrent protection devices be readily accessible and properly labeled. The National Electrical Code Article 406 details receptacles, snap switches, and faceplates. This article provides requirements for the installation of receptacles, snap switches, and faceplates in electrical wiring. Receptacles are the points where electrical power is drawn from the wiring system. Snap switches are used to control lighting and other electrical equipment. Faceplates are used to cover receptacles and snap switches. The National Electrical Code specifies the types of receptacles and snap switches that are permitted for different applications, as well as the installation requirements for receptacles, snap switches, and faceplates. It also requires that receptacles be tamper-resistant in certain locations, such as dwelling units and child care facilities, to prevent electrical shock hazards. Let's talk about equipment grounding and equipment bonding jumper. Grounding electrode conductor connections must comply with National Electrical Code Section 250.64. Connections to grounding electrodes must be accessible and made in a manner that ensures a permanent and effective ground. Bonding jumpers are used to connect metallic parts of the electrical system together to create a low impedance path for fault current. The National Electrical Code Section 250.102 provides requirements for the sizing and installation of equipment bonding jumpers. Equipment bonding jumpers must be sized based on the size of the circuit conductors and must be installed in a manner that ensures a reliable electrical connection. Another topic for focus is GFCI protection, which is ground fault circuit interrupter protection. Ground fault circuit interrupters are devices that are designed to protect people from electrical shock hazards. A ground fault occurs when current flows through an unintended path, such as through a person's body, to ground. Ground fault circuit interrupters are designed to detect these ground faults and interrupt the circuit quickly to prevent electrical shock. The National Electrical Code requires ground fault circuit interrupter protection in certain locations such as bathrooms, kitchens, and outdoor areas. The National Electrical Code Section 210.8 provides specific requirements for ground fault circuit interrupter protection in dwelling units. SI protection, or arc fault circuit interrupter protection, is also important. Arc fault circuit interrupters are devices that are designed to protect against electrical fires caused by arcing faults. An arcing fault occurs when current flows through an unintended path, such as through damaged insulation or loose connections, creating a high-temperature arc. Arc fault circuit interrupters are designed to detect these arcing faults and interrupt the circuit quickly to prevent electrical fires. The National Electrical Code requires arc fault circuit interrupter protection in certain locations, such as bedrooms and living rooms. The National Electrical Code Section 210.12 provides specific requirements for arc fault circuit interrupter protection in dwelling units. For surge protection, the National Electrical Code Article 230.67 covers surge protection for dwelling units. This section requires surge protection to be installed in dwelling units to protect against transient voltage surges that can damage electronic equipment. Surge protective devices must be installed at the service entrance and must be listed for surge protection. Another area to consider for residential dwellings is swimming pools and spas. National Electrical Code Article 680 provides requirements for electrical installations in swimming pools, spas, and hot tubs. This article covers topics such as bonding, grounding, ground fault circuit interrupter protection, and wiring methods. The requirements for electrical installations in swimming pools, spas, and hot tubs are very stringent due to the increased risk of electrical shock hazards in these locations. In Westchester County, New York, The average GPS coordinates are approximately 41.1220 degrees north latitude and 73.7949 degrees west longitude. These coordinates are only approximate and can vary depending on the specific location within the county.